Hi, welcome back to the lecture series on GPU architectures and programming. So, we will just revise once again our previous coverage. So, if you remember, we have been talking about how to build the dependency graph for a CNN style computation, and in general we also visited how the math for back propagation works. And what we could see is that in general, if we have a cascade of layers and we are trying to compute some error term for a specific layer. So, in general, the way we compute it is that is basically you have to multiply the error term that I figure out the delta 2 for the previous layer, multiplied by the weight of the previous layer and the gradient of the activation function in the given layer, right. And so, and this in general would continue, and this gives me the error term, and you multiply that error term with the previous layers, whatever is the input with respect to that current layer. For example, if it is the input layer, then you multiply the currently computed error term with the input matrix. In general, if it is the any intermediate layer, then the error term gets multiplied with the previous layer's output activation, right. So, with that what we figured out was that if we look forward, that how the pipeline computes the different indices that we discussed earlier, and we thought that let there be the following kernels, any kernel KFI which computes the forward the activation output AI of some ith layer, some kernel KB1I which computes the error term, right. Now, one important thing, if you notice in this picture, for the error term we are writing it delta L minus I minus 1. The reason is we are considering L number of layers, and if you remember, the error terms are computed backward, right. So, the last one would be for you put I equal to L here. So, that would give you delta 1, that is the error term for the last layer that you get. So, so that is why for every kernel in some ith layer KB1I, it computes delta L minus I minus 1 as per our indexing for this picture, right. And we use this to compute the overall loss, that is del j del wi, right. And that is computed by so that something that we are representing by dwi here, and that of course is basically the computation of the error term delta multiplied by the previous output previous activation input, which would be this in general this A transpose times delta 1, this kind of a computation. So, that is what is done by this KB2 type kernels here. So, if you look into this picture in the forward pass, so we have I am just reintroducing this picture again after our last lecture, because there is some linkage here which we need to mention, that as you can see for every layer I am introducing this index, right. I mean, although the kernel is kf which is always computing the activations AIs, right. For the ith layer I call it KFI, for the next layer it is KFI plus 1 and so on so forth, right. Basically it is the same kernel which is getting called multiple times, right, for computing the output of different layers, right. And in the backward computation we have two types of kernels here, one type of kernel for computing the error term, right, which is always outputting the delta terms, as you can see. So, I am outputting the delta terms for every KB1 type kernel I am outputting the delta terms, and then for these delta terms are used by these KB2 type kernels to give me the differential loss, right, the differential weight, so essentially is basically multiplying these deltas with the A transposes, right. So, that is why the dependency is from the delta, there is a dependency, input dependency, and there is also a dependency from this A L minus 1s, right. So, they are giving me this the dwi terms, which I will add to these w's and update them and again run the forward propagation, and that will be again followed by the back propagation, right. So, pretty simple. If we now progress with this, this was our task graph view. So, essentially as we discussed that this part is our set of kernels which are doing the entire computation, but it keeps on repeating, right. The computation is a sequence, forward pass, then loss computation, then backward pass, right, and then again it repeats. Again the backward pass outputs are used to update weights, and then again you run the forward pass, and then the backward pass, so on so forth, right. So, with this what we figured is the most important computation we will be requiring is the GEM computations for this kind of neural network trainings. So, overall our observation had been that for doing this GEM computation, we will be recurring to use our parallel programs, and the major scientific libraries that are available, for example, BLAS and the modern term CU BLAS, they actually use these Fortran based ideas that for doing the matrix computation you assume that the data is in a column measure format. Now, what would that really mean? Let us understand. So, like we discussed that whenever we are talking about column measure format, one of obvious thing is that consider the matrix in every ijth term in your mathematical matrix becomes a can be accessed with a ji index, considering that this data is stored in the column measure format, right. And as you can see, that is what is happening. So, you are multiplying two matrices of dimensions m cross k with, and so this is for A, and for B the dimension is k cross n, you are multiplying them. So, you see the access expressions are a bit different, right. So, we are more habituated to writing that well I will have a loop where I have this k iterating, right, for a fixed m, right, so essentially the way we do it is I will have m times some small m, which is the dimension, right. So, if I am so m times small m plus k multiplied by b, and the index for b would be of course the column index. So, k times some capital K plus n, something like that, but as you can see that it is opposite here. The reason is this column measure format, like we already discussed. So, one simple way to think would be that well just consider the data entries, the whatever is your actual ijth mathematical data in your computation, it can be accessed with once you flip the indices with J and I, right. But just to have a more clear picture, consider the real arrangement of the data. Like as we know that we are going to now have that in memory you have everything stored in a consecutive block, and for our usual C or similar style languages we have row measure format. That means, you have a row followed by the second row, right, in that way. But now, since we are considering column measure format, what does that really mean? So, consider some matrix A, right. So, you have the usual, this is a normal mathematical matrix we are trying to write, right, and you have the data of the row 1, row 2 and all that, but when you are storing it, you are not storing it in a C style arrangement in the memory, but rather you are storing it in the column measure format. So, if I just write the data arrangement here, so you are going to store the first column here in the first row, right. So, that means, you are essentially storing A, let me use the 0 indexes here, because finally, I will be writing a C program to access them, A 0 0, then the second element in the column, right. So, A 1 0 like that, and finally, you will be having A m minus 1, this is capital M, the dimension, right, m cross k we are considering. So, m minus 1 for the 0th column, right. move on to the next. So, A for the second column, right. So, that was A 0 0. So, now, so if I just write it, you have A 0 0 here, I have A m minus 1 0 here. The next would be, so A 0 1, and in this column what do you all have? You have A m minus 1 comma 1, right. So, A 0 1 and it all ends with A m minus 1 1, right. So, that is how it is. So, now when you are really trying to access the data, as you can see that you are going here for what element? You are going for some mkth element, right. So, what would be the location for the mkth element? That is the problem, right. So, as you can see, for the mkth element, for getting into the mkth element here, what do I really need to do? Well, I have to make capital M number of skips over this data, right. So, I want some access here mk, right. So, this is this is capital M, right. So, I have to shift to the kth column, that means I have to skip through this k times m number of elements here, right, and then I get to the column where I have the mkth element, right. So, for that, as you can see, I have to multiply k with capital M, that takes me to that position where I have it, right, in that column. Now, the elements of that column are located like this, right. So, I have A 0 kth element, A 1 kth element, like that up to A m kth element. So, that is why the shift by m, right. So, I am just trying to make it clear that, well, it is very simple that you just flip I and j the indexes, but physically in terms of the memory storage, this is what it would mean, right. You have to multiply k with capital M, since you are shifting over k hops of columns here, right. So, with that, this would be our normal code for the J multiplication, where I am also assuming that we will do some tiling based optimization. Now, of course, we are familiar with tiling based optimizations for matrix multiplication. So, this is basically that code only. So, what do we really do? We use a matrix multiplication kernel. We compute the rows and columns, which are the for the thread ID x and thread ID y, right, and we use them to figure out the what is the global row and column value. So, in general, if you recall our idea of doing the normal matrix multiplication. So, every thread we are going to launch a block of threads. Every thread block will try to compute the elements for a tile, right. Inside a tile or in the corresponding view for a block of threads, every thread is trying to compute one element in the tile, right. And what was the way that we progressed? So, if you just remember, let me just redraw the picture again. So, let us say this is your B, this is your A, and you are trying to produce an output matrix C here, right. If you break it to tiles, so tiles indirectly define the way you are going to launch the thread blocks. So, for one block of threads, you are corresponding to computation of one tile. So, every thread, the thread which is going to compute this element will it will have to do a computation of elements here. It has to essentially multiply the elements here with the elements here, right. And how does it really do it? Well, it does it by coordinating with other threads. That means, for this the thread is first responsible for loading this data it will be using two shared memory locations, right. It will be using two shared memory locations. So, it will use this shared memory location to load this data point. It will use this inside this shared memory, it will be loading this data point. All the other threads in the block will be loading the other thread data points. Once that is done, this thread is supposed to now, if you look back into the code. So, this is the position where all those loadings will be done, right, by all the threads collaboratively. Now, once so here as you can see, so we are in the first iteration of this loop, all the threads have loaded the data of the first tile, right, and then they go to this second loop here. In this loop, what is going on? Now, this thread is going to compute a multiplication of the data which has been loaded by all threads here with the data that has been loaded by the every thread here, right. So, this multiplied by this. So, that gives it a partial sum. In the next iteration of the outer loop, again all the threads in the block will load the data for the intermediate this block here and then this block here, and then again every thread will perform the corresponding activities. So, that now after it ends, the thread which is here has performed the partial sum of data up to this much and up to this much, right here, and it continues like this. So, that was our idea of tiling. So, just a small recall here, right. So, if you remember, so this is the position where one thread is loading two data points into the shared memories A sub and B sub, right, and it is waiting here for every other thread in the same tile to do the load, and then it is falling into this loop where it is progressing with all the data in that row for A sub and in that column of B sub to do the computation of the partial sum, right. And once everything is done, like once the thing is done for all the tiles, it will update into the global memory, right. So, that is how things were going on for a normal tiling. Now, again if you remember that since this is the column measure formatting, so as you can see the access expression here for A sub and B sub is just reverse to what we have been seeing earlier, right. So, that is why the iteration k comes first, right, because it is in the columns now, right. So, that is why it is A sub k row instead of A sub row k, and similarly B sub column k instead of B sub k column, right, is just the opposite from earlier. Now, earlier if you remember, we were happy with the result of this kind of a tiling based operation, right, this kind of matrix multiplication kernel with this kind of tiling, we were happy with that, right. But now, we will try to see whether this can be accelerated further. Reason? Well, of course, we have understood that this is the most important operation for neural network trainings, and it is also for going to be popular with many other kinds of workloads. So, this needs to be optimized, right. So, right now all our efforts would be in terms of optimizing this GEM kernel. Now, just I will just point out once again that the difference when we are speaking specifically with respect to the GEM operations for the CuBLAS or similar kinds of libraries for linear algebra, we will be using this row measure representation, right. We'll because that you need to remember that, because that is going to also play a role in our understanding of how things are going to happen here. So, for A sub k comes first followed by row, for B sub you have column followed by k here, right, instead of the reverse that we will be expecting in general to happen. Because let us understand that why is this important? Well, that would mean that the way that the data is getting accessed is a bit different, right. So, that means here when I am accessing the data, what is the access from? The access of this data is from shared memory, right. The access of this data, this is a global load to shared memory, this is a global load to shared memory. This is a load from the shared memory to the internal registers for doing the fused multiplication and add, right. This is a call to a fused multiply and add unit which is there in the GPU, right. Now, these global loads are going to take their own time, right. Now, again as we know that one of these loads will be coalesced and the other will be not, right, because one of them will be row wise and the other will be column wise. So, try and figure out which one is what, right. But here as you can see, this is for from the shared memory to the global to the fuse multiply and update unit, fuse multiply and accumulate unit with the output going to a register of type ACC. I mean the variable name for the register is ACC here, right. Now, if you try to analyze that how this program performs, let us just have a look into the intermediate code or the PTS code that will be generated for this kernel. So, this is a peek into the PTX code for the inner loop lines 14 to 15. So, that is it, right. So, this is the inner loop. As you can see, we are doing two shared loads from the shared memory, because of course, A sub and B sub are in the shared memory, and we are then engaging the fuse multiply and add units, right. So, in each iteration of the loop, per thread activity is as follows. You are doing two shared loads followed by one fuse multiply add operation. Again, in the next iteration of the loop, you are doing two shared loads and the real operation you are doing is one fuse multiply add. So, as you can see that it is basically like only one out of every 3 instructions is useful for computation, but the other 2 are for memory accesses to the shared memory, right. So, if I assume that I have a significant number of fuse multiply add units, well, they are not really getting used, right. So, fundamental reason is that I have lesser occupancy because I am not making good use of the number of threads I have launched. Rather than that, I can make full utilization of the GPU bandwidth by increasing the amount of work that I am delegating per thread. Because here as you can see, the per thread activity I am delegating is one addition of fuse multiply and addition operation for every 2 shared loads, right. We will like to increase it. How would that be possible? So, for this we will perform, we are just trying to apply our thread coarsening techniques that we have seen earlier, right. So, fundamentally what we are really trying to do, now we will try to ask that, well, even inside a tile, I need not have a same number of threads in the block as is required for computing the number of elements in the tile. Rather than that, in my thread block launch, let me have a smaller number of threads for computing the entries of the entire tile. That would mean, now for one thread, I am not just delegating it the activity for computing one final output in the matrix, but rather I am asking you that you compute more than one entry in the final matrix, right. So, if I just draw a picture, it would be like this, that let us say this is my final output and I am going to launch tiles and all that. So, earlier whatever was the activity for one thread, let us say I am asking one thread to do the computation for 2 elements, or in general maybe more than 2 elements, right. So, that is the amount of, that depends on what is my amount of coarsening that I am pushing into the thread, let us say 8 elements, right. So, we will see how it makes progress. So, now as you can see, I will introduce a variable WPT, work per thread. So, of course, one thread will be now accumulating values for more than one output. So, instead of keeping ACC as a single value, single local variable which maps to a single local register for per thread, I will make it an array ACC WPT, so that the thread is accumulating values for multiple outputs, right. And then I hope you can understand things are going to be simple. It is like, so earlier you had this loop, let us just compare with the previous and the current implementation. So, earlier you had the outer loop where you were doing the loads followed by the compute. Well, you still have the outer loop, this is your, so this is a simple loop just for initializing the ACC, right. This you are just initializing the ACC here, initialization. but then this is your normal loop of the previous work. But here earlier you were just doing two shared loads, right, this one and this one. Now you are doing those two shared loads inside this loop. This loop is running from 0 to WPT minus 1. That means you are performing that many shared loads for both A as well as B, right, and you have to compute the shared load indexes by looking into the values of the offsets and all that, which I think you can easily figure out, right. Just to understand that for per thread activity we have increased the number of loads here. Well, how does that help? Because till now we have not seen how the compute increases per thread, because we have increased the number of loads per thread. Well, now let us look into the compute part. So, after the loading is done, here you have the compute. Earlier your compute was just this loop followed by this multiplication, right. But now inside this loop you have another loop where you are doing this multiplication. So, earlier what was the situation? Let us say for this entry you are computing this multiplied by this, right, but now you have two entries. So, you are going to compute this multiplied by, for one thread the amount of activity is, let us say you have 4 entries you are going to compute by this thread. So, you have to load data from here, and I mean you have to multiply the data from here along with the data from all these 4 columns, right. So, that is the per thread activity you have inside this loop now, right. That is why you have this internal loop. But what is the beauty of this internal loop? The beauty of this internal loop is that, of course, here when I am drawing I am using the normal matrix representation, you have to just switch it accordingly, because as you can see that the indices are again in column measure and all those formats. But if we are trying to understand, then as you can see that when this loop is making the computations for these 4 points, it can take one value here, it has to multiply that value with the value here, here, here and here, right. So, one load of this, multiple loads of data from B sub and that many number of multiplications. Go to the next iteration of the loop, one load from A sub, multiple loads from B sub, that many multiplications, right. So, that is the good thing, right, because since you are delegating more activity for this thread, for that one load is common for multiple loads of data from the other array, right. So, that is the good thing, since this is constant you have less number of loads at least for one of the inputs, and that increases your per thread computation now. I hope this is clear. So, the first good thing is you have quotient the amount of activity per thread, and the quotienting is more for the compute part rather than the load part. So, if I just compare it with the previous implementation, the amount of loads from shared memory to the registers for doing the fuse, multiply and add are drastically getting reduced by a factor which is the thread quotienting factor. If you compare the number of loads here, so this is the PTX considering that you have quotient with a value of 8. So, for 8 iterations of the inner loop, what is going on? You load this A sub once, you have to load B sub 8 number of times to achieve 8 number of fuse, multiply, adds, right. Earlier the number of loads was 8 plus 8, but now it is 8 plus 1, right. So, this is not the inner 8 iterations of inner, is basically the innermost loop actually, fine. So, with this optimization we will be ending this lecture, and in the next lecture we will see some more optimizations. Thank you.